Today we are talking about implicit differentiation. And so up till this point we have been differentiating or finding the derivative of explicit functions. So explicit functions are examples are y equals the square root of x squared minus 9 and y equals x squared plus 4. What these have in common is that they are explicitly solved for y. Y is a function of x. Now, implicit differentiation, this actually allows us to differentiate things that aren't functions, okay? So they don't have to be a function for us to find the instantaneous rate of change somewhere. And so we can still use a process called implicit differentiation. And we use implicit differentiation when we have functions that aren't explicitly solved for y. So I have y squared here, and I might be tempted to think, oh, well, I can just take the square root, but I have this additional y here, and so that makes it more complicated to solve for y. In some of these functions, I wouldn't be able to do that, okay? So, but we can still find the derivative of things like this, okay? So we can use implicit differentiation. And so when we're using implicit differentiation, basically, we can do the derivative with respect to x. It's just that we're going to treat y like it's a function. And so this section is after the chain rule on purpose because we treat y as a function of x. So when we take the derivative of it, it's like the outer function with an inner function that you can't see. So we have to multiply by the derivative of it. Okay. So when I'm doing the derivative, so I just have, this isn't an equation or of anything, I just have some different terms here that we're going to differentiate with respect to x. So this is the variable that we're doing the derivative with respect to. And so when we're approaching variables that match, right, this is x to the fourth, then this is a normal power rule situation. So this first term is just 4x squared, or 4x cubed, I'm sorry. Now my next one is y to the fourth. Now I'm doing the derivative with respect to x. Y, unless it's explicitly stated, is not just a constant or a variable, right? It's actually, we treat it like it's a function. And so the chain rule says that we would take the derivative of the outside with the inner one in place, and then we would multiply it by the derivative of the inner function. Well, we don't really know what the inner function is, so we take the derivative of the outside, which is 4y cubed, and then we multiply by the derivative of the inside. And we're going to use the Leibniz notation. So this is d, the name of the function is y, over d, the variable. So I multiply by dy dx. And I do that anytime I'm taking the derivative of y, not when I see y, but when I'm taking the derivative of a y term. So my next term here is negative 4x, that's normal x, so the derivative is just negative 4. And then my last term is 2y. So y again is a function, so I take the derivative of the outer function, which is the 2y, which is 2, and then I multiply by the derivative of y, which is dy dx. All right, so let's look at a little different one. Okay, so again, let me say it again, right? We take the derivative just like it was an x term and just multiply it by the derivative of the inside, which is just implied. So now this time I have xy squared. Again, just one term. I don't have an equation. We're just practicing right now. This, I need to make sure I understand, is a product. So I need to use the product rule. Now, I know that we started out doing this, and maybe you're better with the product rule now and you don't write it out twice, but when you're looking at implicit differentiation for the first few times, I highly recommend that you actually write this out like a product again. Remember when we did this the first time and I said, okay, I'm going to take the derivative of that term and then that term. Hopefully at some point you get good enough that you don't need to do that anymore, but with these, until you get some practice under your belt, I think it's really wise to write this out. So this time I'm taking the derivative of the x term. The derivative of x is 1. So this first term is y squared, because I'm not going to write the 1. It's implied here. Then on this side I have x times the derivative of y squared. The derivative of y squared, you know, the outer function is the y squared, so the derivative would be 2y, and then it's y, So I multiply by the derivative of the inside, which is dy dx. So then I could clean this up a little bit and just call it y squared equals 2 xy oops, not y, it's not equal, so it's plus dy dx. Okay, so there's a technique. So what we just did was we were just doing the derivative of a couple of terms. So when we're doing the derivative and we want to find dy dx for a given equation, then this is kind of our step-by-step process. We do the derivative with respect to the given variable of both sides, right? It's usually x, so we are going to do the derivative with respect to x. We would say, written, that would be d dx of both sides. Then, assuming we're using x as our variable, we collect all of the dy dx terms, or whatever this looks like here, on one side. So all the non-dy dx terms go to the other side. It's like we're solving an equation. Then we factor out the dy dx and solve. Okay, so we're going to walk through the process. So again, this is the important part. When the variables agree, we just use the power rule or the product rule, or basically the simple rules that we've done before. But when the variables disagree, right, if I'm doing the derivative with respect to x and I come across a term with y in it, then I need to, whenever I take the derivative of the non-x, I need to apply my chain rule. Okay, so let's look at our first example of an equation. So I have y cubed plus y squared minus 2y minus 4x squared equals 6. And I want to find dy dx. So I can't just solve for y. I might be tempted to if it was easy. So I'm going to have to use my implicit differentiation. So when I take the derivative of y cubed, right, if this were x, the derivative would be 3x squared. So this is 3y squared, but in fact it's not x, right? What I'm doing here, I should probably write this, is I'm doing the derivative with respect to x at both sides. So 3y squared, but y is not a constant, it's a function, so I multiply by dy dx. D, the name of the function, over d, the variable, and we're given that we're going to do it with respect to x. It's always, this is respect to. That's the variable we're differentiating with respect to. All right, so now we have another y term. So I have y squared, so I end up with 2y, like a normal derivative, right? dy dx, because my variables are mismatched. This x does not match this y. And I have minus 2y, derivative of 2y is minus 2, and it's y, so I have dy dx. At last, the next term, minus 8x equals, and then the derivative of 6, that's a constant, it's equal to 0. All right, so we did the first step. We did the derivative with respect to x, right? So now the second one says we need to collect all of our dy dx terms on one side, and we're going to move all the other ones to the other side. So all three of these, right? Actually, I don't even have to move any of them. They all have dy dx in them. But this is a non-dy dx term, so I'm going to add 8x to both sides. So I'm going to get 3y squared dy dx plus 2y dy dx minus 2 dy dx equals 8x. All right, now I'm going to, the next step then is to factor out, we're in step 3, factor out dy dx. So it's in all three of these, so I factor out dy dx, and I end up with 3y squared plus 2y minus 2. This is equal to 8x. And so my last step, I'm trying to solve for dy dx, and I just divide by everything that's not dy dx at this point. So my derivative, so dy dx then, is equal to this. So again, my derivative, the meaning of it doesn't change, right? So it's still I can find the instantaneous rate of change or the slope of the tangent line at any point using this. It's just that if you noticed, this time, most of our other derivatives when we were doing derivatives of y equals functions, explicit functions, then we only ever needed x to put in to find the derivative. But these actually have a y involved. So if I wanted to evaluate my derivative at a specific point, I would need to plug in both x and y, but that's the only difference really. Okay. All right, so I'm introducing a little bit of new notation the book likes to use, and this is not bad to get familiar with. So we want to find dy dx, and then this line, and this is basically meaning at the point 2, -1. So it's just saying find the derivative at this specific point. That's what we use this. It's dy dx, a straight line, and then sometimes it's a point, maybe it says t equals or something like that. But this is a way to say evaluate this at this place. All right, so again, I probably could solve for y here, but I'm not going to because we're practicing implicit differentiation here. So we're going to find dy dx. So my first step is just to do the derivative with respect to x of both sides, so I'm just writing that. So now I'm going to actually do the derivative with respect to x, so I'm not going to write that again. So 2x, my variables agree, so this is good. Plus now this time I have y, they don't agree with the x, so this is 4y dy dx equals 0. Now I can subtract, so I only have the 1 dy dx term here, so I'm going to subtract 2x from both sides. 4y dy dx equals -2x, right? All I'm doing is this. And I'm going to divide by 4y. And this is my dy dx. So now I wanted to find it at the point 2, -1. So my dy dx at the point 2, -1 is equal to -2 times 2 is my x value over 4 times -1. And I end up with -4 over -4, which is +1. So the slope of my tangent line at the point 2, -1 here is in fact 1, or I could say the instantaneous rate of change is equal to 1, right? All of those things. The velocity is 1 at this point. All right. Just one more word really quickly. If I don't really need dy dx, right, if it didn't say find dy dx and it just wanted me to evaluate dy dx at this point, I actually could have put in the 2 for x here and the -1 for y here and solve for dy dx that way. In the end, I should still get 1, so you can try that on your own if you'd like to. So if it's complicated and you just need the derivative evaluated at a specific point, then once you do the derivative, you can just pop in your numbers and solve for dy dx. That's an alternative strategy. All right, so we are going to write the equation of a tangent line to the graph of x squared y squared minus 9x squared minus 4y squared equals 0. All right, so this time we're getting a little bit more complicated. We need to, before we can write the equation of a tangent line, I need the slope, right? So I have basically a piece of it, right? I have y minus 2 radical 3 is equal to, I don't know why I put parentheses there, but m times 2 radical 3, x, oops, I'm really on the struggle bus right now. X minus 2 radical 3 is what it should look like here. That's the right-hand side. And we just need to find m, right? So this is just your point-slope form. I'm dropping these points, the point into each piece. Oh, that was really terrible. Okay. So I end up with y minus 2 radical 3 equals m times, how about x plus 4 instead, right? That's my x coordinate. Okay. So I need to find this. And to find that, right, m is dy dx at the point -4 2 radical 3. So I'm just using the same notation as before. It's the derivative evaluated at that point. That's always the slope of my tangent line. All right, so we're going to do the derivative with respect to x here of both sides. X squared y squared minus 9x squared minus 4y squared equals 0. Now the right side is easy, right, because this derivative of 0 is still 0. And so this x squared, y squared I'm going to do in phases because I hope you recognize it's a product. So I have x squared, y squared. I'm going to write it out twice, long way. So the first one I'll take the derivative of the x term, the second one I'll take the derivative of the y term. So then I'm just going to go ahead with the rest of the derivatives here. Right? This notation clearly says I still need to do that. So then this will be negative 18x, right? The variables match here, no anything needed. Then minus, now I've got a y term, 8y dy dx. All right, so now I need to finish this off. So the derivative of x squared is 2x, and then the y squared comes with it. Then here I get the derivative of 2, so I'm bringing down the x squared. The derivative of y squared is 2y dy dx. And then I'm just going to rewrite the x minus the rest, minus 18x minus 8y dy dx equals 0. All right, so my dy dx terms are here and here. So I'm going to move these two non-dy dx terms to over here. So I'm going to write my, I'm going to rearrange this one and write 2 x squared y because I don't like them mixed together. Let's just, and then minus 8y dy dx. So these are the terms that have dy dx, these two. I'm just writing them here. Now I'm going to move this to this side. So this is going to become minus 2xy squared, and this will become plus 18x. All right, I'm going to factor out my dy dx here. And then I just get 2x squared y minus 8y is equal to negative 2xy squared plus 18x, and I just divide by everything over here. So 2x squared y minus 8y. And here is my dy dx. All right, now I want to evaluate this at the point negative 4 to radical 3. Okay. So I'm going to write dy dx, and at negative 4 to radical 3 is equal to, all right, so I have negative 2. So sometimes I really have to talk to myself here about which one I'm putting in the right one. So then I have an x, so times negative 4, y squared is 2 radical 3 squared. Then I have plus 18 times x, which is negative 4, all over 2. X squared is negative 4 squared. And then I have times y, which is 2 radical 3 minus 8 times 2 radical 3. Okay, so let's start a new page here. Okay, so my dy dx at negative 4 to radical 3 is equal to, okay, so I can multiply the negative 2 times the negative 4 and get 8, and then 2 radical 3 squared, here, I'm going to write this over here. So if I have 2 radical 3 squared, this is like 2 squared times radical 3 squared. So this is 4 times 3, which is 12. So I'm going to replace 2 radical 3 squared with 12. And then I have minus 18 times 4 is, let's see, 4 times 8 is 32, so 72 over. All right, so now I have 2 times 16 in the bottom times 2 radical 3 minus, I'm going to multiply the 8 and the 2 together. I'm just kind of doing stuff. I could do this more in one step, but I'm just kind of baby stepping my way through it. Now this is equal to 8 times 12, which is 96, minus 72 in the top. Then I have 32 here, times another 2, which is 64 radical 3, minus 16 radical 3. So I can multiply things outside of the radical together, but I can only multiply radicals together. Okay. So now on the top I have, let's see, I have a 24 over 64 minus 16, which is 48 radical 3. So these are like terms. They both have a radical 3. So I can do 64 minus 16, which is 48, and it retains the radical 3. And now 24 and 48 can simplify to 1 over 2 square root of 3, right? Because 24 over 48 by itself would be 1/2. So the square root of 3 is down here. So this is my slope. So now I'm going to come back up here and pop the rest of this in my equation. So I already had, because I was at the point -4, 2 square root of 3, so the rest of my equation looks like y minus the y coordinate, which is 2 radical 3, equals, my slope is 1 over 2 radical 3. You don't need to rationalize, times x plus 4, because my x coordinate was plus 4. And this is the slope of, or that's my equation of my tangent line.